Hello, this is Rob Ellis from Geosoft, and I'm giving a presentation on the Cartesian Cut-Cel method and constrained inversion, the ASCG in Melbourne. And this work has been done with Ian McLeod at Geosoft in Toronto. What we'll be talking about is how to improve modeling and inversion by using Cartesian Cut-Cels. The outline for my presentation is as follows. I'll try and motivate the reasons that we need to go beyond Prism elements, and then I'll discuss some alternatives to the Prism element model. I'll focus on the method which we are advocating, Cartesian Cut-Cel method, and I'll explain why we think this is a good method. I'll demonstrate some applications of the Cartesian Cut-Cel method to terrain modeling and constrained inversion, and we'll also look at an example of the Cartesian Cut-Cel method modeling the base of salt problem, and then we'll make some conclusions on the basis of the results that we've seen. So to illustrate the need for going beyond Prism elements in modeling, we're going to consider the San Nicolas deposit. We have a fairly common scenario here. We're exploring under cover, about 200 meters of cover. This is a massive sulfide deposit, and it's in relatively flat terrain. It's located in central Mexico, as shown on the right. The things to note in this at this deposit are we have a deposit model which has been produced by Myra Geosciences, and the important components of this model are to observe that there's a rhyolite dike which runs through the model here, shown in brown, and the mineralization shown here in red, and there are a number of other layers of rock material, volcanics, and cover in this area. So to give you some more detail about the deposit, it's about 280 meters thick, 900 meters long, and about 300 meters wide. As I mentioned, it's about 200 meters below surface. If you look on the right, you'll see lithologies that are involved in this deposit, and you will also see the physical properties which are, have been assigned to each of those units. And the important thing to note is that all these lithologies have a certain susceptibility. In fact, the cover has a susceptibility of 0.005 SI. The deposit itself has a susceptibility of 0.01 SI. So this is a magnetically more difficult exploration problem. Now, when we're doing geophysical inversion, modeling or inversion, we need to take our geologic model, which is usually defined in terms of surfaces, or for example, even the true Earth has a relatively smoothly varying terrain here, and we need to voxelize it or turn it into a voxel model. And you can see that that process has been undertaken here, and I've taken this deposit model and turned it into this voxel model here, and you can see this rhyolite dike on the edge here, which is this edge over here, and you can see that the terrain, which is the important point for this discussion, is now represented by large flat areas with a step up of one layer of voxels, and then another large flat area, and then a step of voxels, and so on across the model. So it's relatively flat here. These voxels are 20 meters in size, so you can see that the entire terrain varies maybe 60 meters across this survey. Now what I've done is blown that image up around the yellow arrow here, and you can see what is happening in our voxel model. It's quite a fine discretization, and as we step along, we cross a transition point, and we have to step up another voxel, another prism thickness, 20 meters, and then continue on. So this is the way that the terrain is represented in the voxel model, and I'm showing here the true terrain. Now, what we're going to do once we have this model is we're going to use it and we're going to calculate the RTP response over the top of the model for a typical airborne magnetic survey, and we're going to see what the response is to this particular VMS deposit and this geology. So we're going to see if what we can see in that response. So we do that, and what I'm showing here is the result of that calculation, the RTP response over the deposit model at different heights, and so different clearances. So the first image here is with a clearance of 1/2 a cell, which in this case would be 10-meter clearance, and you can see this very strange result, but if you look at it you'll soon see that this result actually maps out exactly the steps in the voxel model in the terrain. So really all we're seeing here are terrain artifacts. Next, on the right, we've stepped up to 1 cell height above the model, and we're still severely contaminated by voxel terrain artifacts. And so we go up to 2 cells and we see again 40-meter clearance. We're still corrupted, and at this stage the magnetic response is about the range of the RTP response is about 43 nanotesla. We go down to 3 cell clearances. We're still largely corrupted by these terrain effects. 5 cell clearances, so now we're at 100 meters above our model, and now the RTP response has dropped down to about 24 nanotesla, and the terrain artifacts are still clearly evident. Now, going to 10 cell clearance, or 200 meters, we have started to see that we're no longer affected by these terrain artifacts. So effectively at 10 cell clearances or 200 meters above the surface, we're able to more or less accurately model the response of the deposit. But at this stage the response has gone down to 16 nanotesla, and you'll notice in this that we're not seeing any real evidence of this rhyolite dike which was running through the model. It should run through about here. So this is showing us that if we're using a prism-based model, we really need to be about 10 cells above the model, a clearance of 10 cells before we can avoid serious prism artifacts. Also draw your attention to the fact that the RTP response is effectively the same as the gravity gradiometer response, the GZZ response, via Poisson's relationship. And for example, at this 5 cell clearance or 100 meter clearance, we're talking about 100 ETVOS range in GZZ. So that gives you some idea of the size of these artifacts for a gravity gradiometer survey. So that's 100 ETVOS range. So you can clearly see that we have a problem using prisms to represent topography, and we need to go beyond that. So now let us look at possibilities for going beyond the prism model. And there are a number of possibilities which are relatively popular at the moment. One of these is, of course, the octree method. This is a method for going beyond a prism response, and the way the octree method works is by potentially recursive subdivision of each prism element into 8 sub-elements, so that you have something which is similar to that shown here. If this green curve represents the terrain, then on the extreme left we have the regular mesh with this problematic step every so often, with the octree method dividing these prism elements which are intersected by the or cut by this topography, we can see we're getting a better representation of the terrain. And on the extreme right, we have another method which is to move to an entirely unstructured grid. Usually these are tetrahedra in the three-dimensional case, and we can see that you can do quite a good job of representing the surface with the unstructured mesh. In between those two, I'm showing the Cartesian Cut-Cel method that I'm presenting and advocating in this presentation. And the way the Cartesian Cut-Cel method works is that any voxel which is a prism element which is cut by a surface is effectively cut into two parts, a part in this case beneath the surface and a part above the surface, and so you can therefore represent any geometric surface by modification of a small number of elements, turning them into what are called Cartesian cut-cells. And you'd ask, why do we like this method? Well, one reason is that it's a minimal extension to a regular mesh geometry, and we like the regular mesh geometry because we have a large number of libraries and tools for dealing with regular meshes. So the fact that we leave the majority of the mesh regular and are able to represent the surface by modifying a small number of cut cells is computationally efficient and uses existing libraries. The other thing is that there are many advances being made recently in constructive solid geometry in the computer graphics world, and we're able to leverage off those developments in the process of cutting voxels. What might have been a tedious and slow process at one time has now become quite efficient and straightforward thanks to the computer graphics industry. So this is the method we're presenting and talking about today, the Cartesian Cut-Cel method. To show you how that works in 3 dimensions, I'm showing you an example here of a survey over a smoothly varying smooth hill, and you can see the survey locations here shown by the orange points, and the hill is represented by this green model. And what you can see in the model is there are flat surfaces in the model, and these would be the top of a voxel or prism mesh. And what we're going to do is we're going to fill in, if you like, a set of cut cells over the top of these prism elements to make the entire surface exactly conform to the terrain. So I'm showing you one element here. As I zoom in on that, it'll become a little clearer. You can see here the element, the tops of these surfaces would be the voxel model representation. We are adding these particular cut cell components to the model, and therefore in that process generating an exact representation of the topography. Zooming in a little further, here is the element again, and what we're left with is, when we're doing our computations to calculate any geophysical response, we are left with the response from the prism elements, which we're all familiar with dealing with, plus now we have a small subset of the polyhedra from which we also know how to calculate the response, and we can do that and therefore calculate an exact response based on that. So coming back to our example from San Nicolas, this is the type of model that we had if we're just using prism elements. If we use these cut cell elements to fill in the topography correctly, then we need to run over the top of this model and construct these cut cells as I've just demonstrated and add them into our modeling and inversion as extra elements. So let's see what the effect of that is. Coming back here again, remember the San Nicolas model, we're looking at the terrain in that model. I mentioned to you that there's the ore zone and there's this rhyolite dike coming through. This was the representation we had when we voxelized the model, and here was the slide. It was exactly the slide I showed before. But here what I'm showing you is the Prism RTP response. This is the same set of images across the top that I showed you before at a clearance of half a cell, 1 cell, 2 cells and 3 cells. So this is 60 meter clearance, this is 10 meter clearance. And underneath I'm showing you the RTP response that's calculated when you incorporate the cut cells into this model, so that the cut cells now allow an exact representation of the terrain. And you can see there's a very marked difference between those two, as you would expect. Now we're getting a very nice representation of the model. We actually see very clearly the magnetic signature of the rhyolite dye coming through in each of these, and so even at 10 meter clearance we're getting a good model with no evidence of any terrain artifacts. And you can see as you step up higher and higher in the model, up to 60 meters is really just the transition that you would expect from upward continuation of the data. Now moving to 5 cells and 10 cells, these are the images before. I found that where I argued that at 10 cells or 200 meter clearance we were almost free of these terrain prism artifacts, and that's verified here by the Cartesian Cut-Cel method when it extends to up to 10 cells, and I repeat the calculation, I start to see that these two methods give exactly the same response, which is what you'd expect. So or very similar responses anyway. So this is confirmation both of the method and the argument that you really need to go about 10 cells up. You can see at 5 cells clearance you're still seeing a terrain artifact. Okay, so that's an example of the terrain response. How does this come into play in inversion? Well, it's particularly important in constrained inversion. A common enough scenario in inversion or constrained inversion is that we know something about the cover rocks. We perhaps have their thickness determined by some other geophysical method or some drilling, or we've got some fairly convincing arguments that the cover thickness is limited to a certain depth. And in this instance, at San Nicolas we know there's about 200 meters of cover, and we know that the susceptibility of that cover rock is about 0.005 SI. So we're going to now say, okay, if we know this cover sequence and we know its susceptibility, we're going to use that in our inversion, and we're going to invert for this ore zone. We're going to invert and see how well we can image this zone, and we're going to do it with in two cases. One, I'm going to use prism elements in the inversion, and secondly I'll use Cartesian Cut-Cel elements to represent the terrain. So then we'll compare those two. So the important thing is that in this constrained inversion this cover sequence is assumed known, and what I'll show in the following images is a slice through this inversion result, a plan view slice through the inversion result at this depth, which sort of slices through the ore zone. Alright, so here is the result of that inversion process. I've inverted, and I'm showing on the top what the slice from the inversion looks like if I invert with prism elements, and underneath that I'm showing the slice that is recovered if I invert using Cartesian Cut-Cel elements. So you can see here that if I use prism elements, what has happened of course is that the artifacts from the surface, the constrained surface, have forced the inversion to somehow compensate for them by putting variation in the model at depths to compensate for the errors that are associated with the incorrect computation in the upper surface. On the other hand, because the Cartesian Cut-Cel method allows exact computation of the surface, it is not affected by that, and so it's able to produce the correct inversion result. And here's the rhyolite dike being inverted, clearly imaged, and this is the ore zone that's we've got. So that's two examples, and both of those examples in essence depended on accurate representation of the terrain. Now in this final example, what I want to do is show you how the Cartesian Cut-Cel method works for subsurface bodies. And here I'm showing you again, supposing this oval represents my ore zone, and I'm trying to represent it in a regular mesh. Well, of course I can only represent it in a coarse manner. I can move to the octree method and represent it more accurately. I can work in the unstructured domain, and you can see that you can represent it quite accurately there. Or I can work in the Cartesian Cut-Cel domain and simply cut these elements where the surface passes through them, and turn these elements into cut cells. So that's the process I'm going to describe in the following example. To make it a little clearer, for example, let's suppose that we apply this process to the San Nicolas ore zone. This would be the ore zone that's determined, let's say, by drilling. And if I were going to represent it as voxels or prism elements, this would be the representation. If I want to represent it as cut cells, then I am now able to actually represent it exactly by cutting these elements in the following way, so that you will now have a series of cut elements representing the voxels. So we're the ore zone. So we're able to represent the ore zone exactly through this process. And why is this easy to do now? Well, I'll just digress briefly here to describe the computer graphics, computer science approach that we use. It's called constructive solid geometry, and basically it allows you to work with Boolean operators on geometric objects. And for example, if I have my ore zone B shown by the blue sphere, and I have a voxel A shown here, I'm able to, with this constructive solid geometry in a computer representation, easily perform various Boolean operations. For example, I can form the union of these two zones, or I can form the exterior voxel component in this Boolean manner. So this would say just give me the host rock. Or if I wanted the ore zone component, I can say I just want the intersection of these two domains. And of course in the computer these are represented, these cut zones like this or host rock cut zone here will be represented as polyhedra, so they're represented like this. And the library we actually use and find very efficient in this case is the Seagull the computational geometry algorithms library. And as I said, this all stems from a number of different applications. In this case, the process of forming bodies for manufacturing is shown here, and an example of well, this is what's called the AABB, the axis aligned bounded box method for determining whether objects are cut by other objects. So there's a lot of work that's gone in this area, and we're able to leverage on that for our inversion work. So what I want to show is an example of using this Cartesian Cut-Cel method for the base of salt problem. The base of salt problem is basically the situation that often occurs in marine hydrocarbon exploration, where we'll have some seismic horizon which represents the top of the salt body. This salt body can be imaged quite accurately, and perhaps under these various flanks of a salt body there'll be an accumulation of hydrocarbons. So these are very interesting areas, and it's very important to be able to map the bottom surface of these salt zones. Now unfortunately seismics has a great deal of difficulty actually imaging through this salt. And for example, this is a synthetic, but it illustrates the problem for this is a salt zone. This is a seismic the seismic section that we see over it. It's imaged the top of the salt zone quite well, and various other structures in the background host rock. And what you can see is that there's really no clear evidence of what happens to this base of salt. Is it a deep keel of coming up here of salt, or is it a closed off? So, and again, we're very interested in what this structure of this salt body is. So we're going to use our Cartesian Cut-Cel method, and because we now have the ability to represent surfaces exactly in the voxel space, we're able to represent this top of salt surface very accurately, and this bottom of salt where it's available, and then we're able to work and use our geophysical method, gravity in this case, to help the seismic interpreter determine what the base of salt is in this particular case. So here on the left I'm showing a simulated salt body, basically a cap of salt, and it has a root or keel of salt coming up, and the question is, if I know this top of salt, can I use for example gravity to help us determine whether or not there's or what the nature of the salt is below this salt surface. Now we're really interested in the Cartesian Cut-Cel method here rather than the base of salt problem. So what I'll show you here is the salt cap, if you like, and we can see how it's represented. I've blown it up here, how it's represented in the voxel model. So we're able to represent this surface exactly using these methods, and the representation of the surface, the way it's done, is completely independent of the mesh density. So it doesn't matter what the mesh spacing is, the representation of the cut surface is exact. So what we're talking about in this case is that we'll have our interpreter's best guess of what the salt is. So perhaps the interpreter's decided that they think they're going to start with the hypothesis that there's just this is just a lens of salt or a cap of salt, and that there is no salt zone or root of or keel of salt coming up into this salt body. Now what we'll do is we'll consider this information, or this, to be a constrained inversion, where the constraint is that this cap of salt it must be present in the inversion result. And then what we'll do is we'll invert for all the other voxel elements in this model space, and we'll use the gravity data over this true model to determine and see if we can determine whether there is a salt root. So this is what we'll be inverting for. We'll be inverting for all these cells M, I, J, K, the voxel elements which are outside the salt surface. So there'll be entire prism elements and a series of cut elements around the surface. And when we do this inversion process, what we have is our salt body, which is the exact representation of the interpreter's initial estimate of salt. And we've solved now for all the cells surrounding this, with the cut cells around the edge of the salt body and the regular voxel elements outside that, and we're able to see when we do the inversion that yes, there is an indication of more salt beneath this salt target. So this information can then be fed back into the seismic interpretation and a better understanding of the distribution of salt, and therefore the likelihood of hydrocarbon prospectivity. So that summarizes, or that concludes my examples of the Cartesian Cut-Cel method. I'll summarize by saying that the method produces essentially artifact-free responses, particularly for geophysical airborne surveys, and in many cases it's sufficient even for surface surveys. It's important even in largely flat areas to use these Cartesian Cut-Cel methods if you want to avoid terrain issues that would occur if you're using voxel elements. In fact, I would argue that in these largely flat areas you're much better off if you're restricted only to a prism-based modeling or inversion algorithm to actually assume the surface is flat and ignore the topography, which will in itself introduce errors, but those errors are probably going to be less than the errors introduced by trying to represent the topography by prism elements. When we start doing constrained inversion and we try to make the inversion more accurate and more realistic, it becomes more important that we model more accurately, and so this is why these Cut-Cel methods or other methods which more accurately represent the Earth are important. I've shown you that any type of embedded surface can be used in this type of process, so we can represent ore zones or salt bodies, faults, doesn't matter, any geometric surface can be represented, and any number of geometric surfaces can be represented in this way. And the nice thing for us is that these type of models work well with existing regular mesh algorithms and display algorithms, and we're able to leverage off of new computer graphics techniques. So we're able to bring a lot of new ideas and new power to this type of inversion and modeling. So thank you. That concludes this presentation. Thank you for your attention.